Alright, hello everybody. This is Rick Wendell's Hobby Electronics videos, and this video is entitled Ohm's Law Formulas, Uncut. And I call it Uncut because it actually includes everything that you need to know, and you can actually start using it the way you should be using it, but probably were never taught. So first thing you got to look at is voltage. Voltage is abbreviated with a symbol, either E or V. That's one of the problems. There's confusion on it. E comes from electromotive force, and electromotive force is something we'll talk about here. V simply stands for voltage. Voltage is measured in volts, and it's always E, so it's electromotive force. Anyway, electromotive force, the term electro in electromotive force, electro, traces back to a Latin adjective called electricus. And electricus refers to the power of amber to attract lightweight bodies when rubbed. So in other words, it has to do with the ability to store a charge when it's rubbed. So another way you could say it is it has to do with the maintenance of the charge, or the maintaining of the charge of the power supply. It's acting as a power supply. So amber is a hard, translucent, fossilized resin originating from the extinct coniferous trees of the Tertiary period. Now that's very important. You got to memorize that for electronics. Typically it's honey yellow in color. The term tertiary was first used by Giovanni Arduino. Arduino is pretty popular in electronics, and he lived in 1759. He classified geologic time into primary, secondary, and tertiary periods, and that was based on observations of geology in northern Italy. Now the names are archaic, that is to say they're old, they're not used anymore, and in this case they've been replaced with an entirely new system. The time period that amber was produced was in between the Paleocene and the Neocene periods. Tertiary also includes the early Pleistocene period, so don't get all screwed up by this tertiary name. That's when amber was officially fossilized. But there's fossilized tree sap that resembles it, and it's also incorrectly called amber. And then there's the manufactured variety. How do you get on the subject of amber? I don't know. But true amber is an earth element. It has a calming effect on you spiritually. It's been known and cherished for a long time throughout history. And you can still buy it for that purpose. The concept of electromotive force is way over most people's heads, and that includes engineers. You have to have at least 2 years of college physics. I would say more like 3 to 4 years to really understand it. Through 2 to 3, maybe 4 years of physics to really understand what they're talking about when they're talking about electromotive force, and really understand it. The problem is the stuff you're being shown doesn't really have anything to do with physics typically. The definitions are incomplete definitions, and that's because they're proposed by industrial engineers that were trying to pretend like they knew exactly what they were talking about. And I can assure you they don't know what they're talking about. They're what we would call invented definitions. They're just made up, imaginary. They sound real complicated, and they are, but they're complicated and they don't know what they're talking about. So it's pretty much the same as if I didn't know what I was talking about. So technicians like me are clueless as to the deeper significance of electromotive force, and I'm willing to admit that. Before electronics became established, industrial engineers were tasked with understanding what creates the constant field, which keeps the potential difference constant while the electrical current is taken away from it. So that's what electromotive force means in terms of simple garden variety power supplies. Excuse me. It's the force that keeps the potential difference the same in a power supply while energy is taken from the power supply. And that's all it means to us. And if you want to use the symbol E for voltage, that's fine, but I'm going to use a capital V for voltage. So be prepared throughout this. You're going to see E and you're going to see V as the symbol for voltage. And either one is correct, really. The reason they call it force now with this electromotive force, the reason they call it force is because the industrial engineers used hydraulics to develop the concept. You'll also hear it referred to as pressure. So you have this pressure and you have this force, and then you get a flow and it's all pressurized and everything, like in hydraulics. So none of this stuff really has any weight to it in terms of making sense. So here's the definition I suggest you use for electromotive force as it becomes more and more archaic in reference to simple power supplies. And I apologize to any physics people that actually do understand this, but us lowly technicians really need a working definition, and engineering is not able to provide it. So electromotive force then would be the force that keeps the potential difference or voltage the same in a power supply while energy is taken from the power supply. And that's really all it is. This would be one very simple definition that actually can be used and makes sense. We should leave the rest of the definitions up to the physicists who actually know what they're talking about. Voltage then would be the potential difference of the power supply. That is to say, the difference between the two charges or terminals. I wanted to explain that before we start talking about the symbols used, and everybody gets all confused because there's more than one symbol being used for voltage. I have some formulas written up that I used E with, and then I got some that I used V, so yeah, anyway. Now if you look at this chart here, you can see that it includes two laws. It's erroneously called Ohm's law. It's actually Ohms and Watts law. I don't know if they were mad at Mr. Watt or if Mr. Watt did something to anger somebody or something, but Mr. Watt came up with what's called Watt's law, and without Watt's law, what everybody's calling Ohm's law wouldn't work because you'd be missing about half the formulas. So all 12 formulas are derived from these two formulas. One of the guys' names is Ohm and the other guy's name is Watt. So if you look online or something for an Ohm's law chart, what you get is an Ohm's law and Watt's law chart, even though it's not specified as such. Now take a look at this chart here. It's actually two little charts. Look at the top one. You have on the left hand column you have VIRP. Those are quantities, and then to the right are the actual units. So you'd have the first one is the capital V stands for voltage, and the one to the right of that is a small v, which stands for volts. So you have the quantity, to the quantity is capital V, and the unit is small v. Okay, so take a look at the chart down below where it says 6 volts. The way you would write that is you would include the quantity V. V would be written, see how does that work? Yeah, you go, I have the X's in there. Those are called subscripts, and you use those quite a bit. If you just had one power supply, you would typically call that power supply V1. So in this case, if the power supply was 6 volts, you'd write V1 equals 6 volts. It could also refer to a voltage drop. So if you had like resistor 3 and you measured the voltage drop, you would write V3 equals 6 volts, like that, like I have it written on the right there. Okay, so the next one in the column is I and then capital A. If you look on the top again, I stands for current. That makes complete sense, right? Okay. The reason why it doesn't make sense is because it's actually means intensity of current, but nobody uses that anymore. Nobody refers to it as intensity. It's actually current, just current. That's it. That's what you need to know. So the next one to the right there is the unit then. That would be ampere, or if there was more than one ampere, it would be called amperes, plural. So let's look down at the lower chart there where I give you an example on the second line where it says 2.34 milliamperes. The way you would write that is to the right. Now you wouldn't write the I sub x, you'd change the x to something that meant something. If you were working with one series string, then the current would be would obviously be the same in all parts of the circuit, so you'd probably just call it I sub 1 and then 2.34 milliamps, and you'd write it in that fashion. Now if you're typing it, that's the way it would look, but if you're writing it, there's a little bit of technique to writing the milli and so forth. If you need any help with that metric stuff, just go back to my series and review it. I have that on series. Anyway, so the next one down on the list is R, which is resistance, and The unit next to it is the mega symbol, and that stands for ohm. So it'll be resistance in ohms. Go down to the bottom chart there, it says 3 kilo ohms. The way you'd write that is R, and then you put some kind of sub number in there to kind of define what it is in the schematic. All these sub numbers would refer to the schematic. I kind of forgot to tell you that. Let's see, to say the resistor 3 was 3 kilo ohms, you'd write R sub 3 equals 3 kilo ohms. Now this one, for some reason, they shorten it up to K ohms. They don't do that with any of the other ones. So you'll hear people say like 3 K ohms instead of 3 kilo ohms. But they don't do it with any of the other ones. Like meg ohms, they won't say meg ohms, or they won't shorten the other ones. They'll be said like normal. So like mega or kilo. Or kilo is the only one that's shortened, and then see, pico and milli. They're all pronounced the same way, except for some reason this K is shortened oftentimes, so you just say 3 K ohms instead of 3 kilo ohms. So go to the top again, we got one left. We got the quantity P, which stands for power, and the unit for power is the watt, and that's the small w. Okay, and so you go down and see how it's written. So if you got a 60 watts and you wanted to write it out, you just write down P sub whatever number equals 60W. And the number would correspond to whatever it was. Like if you measured the power through a specific resistor and it was like resistor 3, then you would name it P sub 3, corresponding to that particular resistor. That way you could find it in the schematic and you'd know how it worked. That's very, very common. Very important to know that. Alright, so the next thing is I prepared a chart, but it was too big to, put on the screen, so I just kind of broke it up into sections, and most people don't understand it, so I kind of got to go through it. So we're going to go through these different quantities and make sure you actually understand what they mean, because most people don't. So first of all, you need to understand what I'm talking about, quantities. And from the chart, if you remember the chart there, I was referring to the first one as quantity. Well, quantity is actually that property of things that is in principle measurable. And that's what it means. That property of things that is in principle measurable. And that's very important you understand that. Most people have no clue what that means. You can go all over the place, all over the internet. Nobody has a clue how that works. Go to the Food and Drug Administration. Look at their website. They have no clue. Of course, I think they just sell drugs now. So anyway, there's the next one, quantity symbol, E or V. We already discussed that. Both of them stand for voltage. EMF stands for electromotive force, but when you just see E alone, that stands for voltage. V stands for voltage. Okay, so the quantity is voltage. And we got two different definitions there. Remember, they're two different things. Electromotive force is not the same thing as voltage. But the E and the V mean the same things. They've come to be known to mean the same things, but in actuality, the E is kind of going away, because it did actually mean electromotive force. Anyway, so that's kind of confusing. Anyway, electromotive force, again, is the force that keeps the potential difference or voltage the same in a power supply while energy is taken from the power supply. And voltage is the potential difference of the power supply, that is to say the difference between the two charges or terminals. Okay, so let's go on to this next part of the chart where we define the unit for voltage. First of all, you need to know what unit means. Most people have no clue what unit means. So a unit is a quantity adopted as a basis or standard of measurement in terms of which other quantities can be measured. So let's take a look at that. That's confusing. We got quantity adopted. Okay, so the thing that we just got done talking about, I'm sorry. So we're talking about voltage. So the thing we just got done talking about was voltage, the quantity voltage, and now we're talking about the unit, and it's referring to it as a quantity. And anyway, a quantity is adopted, and it's adopted as a basis or standard of measurement. So it's just the name of a standard. That's what's important to know. It doesn't have anything attached to it other than the fact that it's the name of a standard. That's what you need to know. And that's it. That's just a name. So you come down here to unit symbol, and it's a small v. That stands for volts. So if you have 1 volt, it would be volt. If you have more than one, it would be plural, which is volts. Okay, and then let's come down to the definition of what volt is. Now most of these units don't have a definition. They don't have. Some of them do, some of them don't. This one, it kind of applies to what we're talking about, and some don't. They don't really apply. So volt would mean to charge something as with electricity, to energize it, or to shock it. Anyway, that's a definition for what it's worth. So the next thing we're going to take a look at, we're going to take a look at the next section here, and you can see the definition of the unit of measurement. Now the unit of measurement makes absolutely no sense unless you write it backwards. I think they were looking in a mirror or something when they saw it and they wrote it wrong. Because basically what it means is, instead of saying unit of measurement, say measurement of unit. So we just got done talking about the volt as being the unit. So now we're going to talk about the measurement of the unit. How do you measure 1 unit of volt? Okay, so basically what it says is it's a definite magnitude of quantity defined and adopted by convention and or by law that is used as a standard for measurement of the same physical quantity. Well, that's really nice. But what it means is it's taking a quantity and it's defining it as a measurement of the unit. You're defining it by coming up with a measurement for the unit, and that's kind of what it means. It's kind of confusing, I know, but that's what it means. And so we come down here to actually defining what the measurement of the unit volt is. So a volt would be defined, it's the difference of potential required to make a current of 1 ampere flow through a resistance of 1 ohm. And that kind of fits the term for voltage. And then this one down here, they're talking about constant current, which kind of applies to EMF. So the difference of electrical potential between 2 points of a conductor carrying a constant current of 1 ampere when the power dissipated between those points is equal to 1 watt. And I wrote down that this definition fits the term for EMF. They're talking about maintaining the voltage, maintaining the potential difference. That's EMF, that's electromotive force when they do that. Anyway, that's how that works. Now 1 ampere is actually 6.25 times 10 to the 18th electrons flowing past a given point in 1 second. You need to know that now. 6.25 times 10 to the 18th electrons is a quantity, and it's represented by the coulomb. So 1 coulomb is 6.25 times 10 to the 18th electron. So if you take 1 coulomb and you have it pass a given point, you just mark a point on the circuit, have that pass that point in 1 second, you have 1 ampere of current. And that's another way to define it. Probably the most common way I've known. And so if you have 2, say you have 6.25 times 10 to the 18th electrons and you triple it, well, now you have 3 amperes. That's how it works. So that's the whole point of me telling you that. Anyway, so let's go to the next one, where we're talking about current. Again, the quantity, we're talking about a quantity. I is the quantity, stands for intensity of current, or just current. The definition of the term quantity is that property of things that is in principle measurable, and that's what I is. Okay, so that would be current, and the definition of the actual quantity is, there's 3 different definitions. 1 is the movement of electrons through a conductor. 2 is a movement of electrons, positive ions, negative ions, or holes. And 3 is the rate of transfer of electricity from one point to another, and we just talked about that, the coulombs of charge passing a given point. And then that's all there is to that. And let's go to the next part of the quantity. Current has a certain unit that it uses, and that is the ampere, so let's talk about that. Again, a unit is a quantity adopted as a basis or standard of measurement in terms of which other quantities are measured. So you're just taking a quantity, it's also a quantity, just like I as a quantity, ampere is a quantity, but it's been adopted as a basis or standard of measurement. So that's how it becomes a unit. It goes from being a quantity to a unit when you do that. So the unit symbol would be a capital A. The unit, of course, is ampere. If you have more than 1 ampere, it would be amperes. The definition of the unit, well, you could say it's a unit of electrical current or rate of flow of electrons. Yeah, the definitions for unit are just really lame, because they don't really define them. Usually they just say, well, it's the SI unit for this quantity, and they don't really know. Anyway, let's go to the next section here where we actually define the measurement of the unit being the ampere. So again, what is the definition of unit of measurement? Well, if you just flip the words around, it makes a whole lot more sense. You call it measurement of unit. That's what you're doing. I don't know why they call it. It's so confusing. I don't know who screwed that up. Man, they did a nice job. So, definition of unit of measurements. The measurement of a unit is a definite magnitude of quantity defined and adopted by convention and or by law that is used as a standard for the measurement of the same thing. So, if 1 ampere equals 2 cookies and you have 4 cookies, now you got 2 amperes. That's what it means. Anyway, so let's go ahead and define what the measurement of the quantity, the measurement of the unit ampere is. First definition would be a unit of electrical current or rate of flow of electrons. 1 volt across 1 ohm of resistance causes a current flow of 1 amp. A flow of 1 coulomb per second equals 1 amp. An unvarying current is passed through a solution of silver nitrate of standard concentration at a fixed temperature. A current that deposits silver at the rate of 1.118 milligrams per second is equal to 1 amp, or 6.25 times 10 to the 18th electrons per second passing a given point in a circuit. Okay. And then 2 would be the constant current, which, if maintained in 2 straight parallel conductors of infinite length, of negligible circular sections, and placed 1 meter apart in a vacuum, will produce between these conductors a force of 2 times 10 to the negative 7 newtons per meter. Okay, and then they're trying to get into force, which is the whole hydraulics thing, so yeah, that stuff is pretty much worthless. I think the 6.25 times 10 to the 18th electrons is kind of what you really need to know, and what 1 coulomb means, because you actually use that. The rest of it's just a bunch of crap. Unless you want to get into the physics of actually figuring it out every time you're trying to build a circuit, you know, I wouldn't suggest you do that. It takes a long time. So, the next thing, where are we at now? Oh yeah, we got to learn about resistance. So, let's take a look at this part of the chart here where we describe resistance. Again, quantity. The quantity is resistance. Quantity means what? That property of things that is in principle measurable. Okay, so we come down here to R, that's the symbol, capital R. And the quantity is resistance, and okay, so what's the definition of the quantity resistance? Well, you get into that pretty heavy here. It looks like the property of conductors that, depending on their dimensions, material, and temperature, determines the current produced by a given difference of potential. That property of a substance which impedes current and results in the dissipation of power in the form of heat. The practical unit of resistance is the ohm. It is defined as the resistance through which a difference of potential of 1 volt will produce a current of 1 ampere. Wow, that is completely worthless. Okay, a current element designed to offer a predetermined resistance to current. Okay, yeah, duh. A ratio of the applied electromotive force to the resulting current in a circuit. It is a measure of the resistance of the circuit to the passage of electric current, and is measured in ohms. Its value is determined by resistance equals E divided by I, where E is voltage in volts and current in amperes. Okay, that is completely worthless too. So, a lot of this stuff is because they don't know the difference between a quantity and unit, so they just kind of throw stuff out there, and when they realize they don't know what they're talking about, they oversimplify it. So, the next thing would be to define what ohm is. Let's see here. So the definition, what's the definition of a unit again? It's a quantity. You're taking a quantity just like we just had there with resistance, and we're adopting that as a basis or standard of measurement in terms of which other quantities are measured. So that's the name. Basically, that's just the name of the measurement of the unit. So you have to come up with this measurement for the unit, but you have to name it, right? So that would be the unit. And so ohm is what you call it. Actually, that symbol is called omega. It's a Greek symbol, and it means ohm. So then we get, what is the definition of the unit? It's the unit of resistance. Ooh, that helps. See, it's oversimplified. It doesn't really help you. They don't know what they're talking about, so they oversimplify the definition. They don't know the difference between quantity and unit or measurement of unit, so So they oversimplify it and come up with these lame definitions. So the definition of the unit of measurement, we already went over that. Basically, we're taking the unit of measurement and flipping it around so it's stated as measurement of unit. It makes a lot more sense that way. It's adopted as a convention or by law, and it's the standard of the same thing. So if you have more than one of those things that you define, then you know you have 2 units, or 3 units, or 4 units. So let's go on here. So how do they do it with the ohm? How do they define it? How do they measure the unit? Well, take the resistance of 0 degrees Celsius. Take the resistance at 0 degrees Celsius, I probably should say, of a uniform column of mercury, 106.3 centimeters long and weighing 14.451 grams. And then I think I forgot to write the rest. Well, it's not important because you're not going to do it anyway, and it's pointless. But there's these standards basically that exist, and you need to know them if you're going to figure out the physics behind the unit. But you have to understand the difference between unit and quantity and measurement of unit before you can actually get into the physics of it, which is called quantity calculus, by the way. So before you get into quantity calculus, you might want to define those terms. So the next one is the electrical resistance between 2 points of a conductor when a constant difference of potential of 1 volt applied between these points produces in this conductor a current of 1 ampere, the conductor not being the source of any electromotive force. Wow, that's completely worthless. Alright, so let's go on to the next thing here. Definition of the term quantity, again, is the property of things that is in principle measurable. And that corresponds to this P here. That's what P is. It's quantity. It's not a unit, it's quantity. And the unit for power is, of course, the watt. And that becomes a unit. It starts out as a quantity, and then it's adopted as a unit of measurement, or a measurement for the unit, and then it becomes what's called a unit. So let's go through the definitions of quantity, of the quantity power. The energy dissipated in an electrical or electronic circuit or component that is conducting either AC or DC. You can see how stupid that sounds, how pointless that is. That's because they don't understand the definitions of what a quantity and unit is. So the electrical energy developed to do work, that's pointless. That's more of that hydraulic nonsense with the pressure in the hydraulic system. Rate of doing work, yeah, kind of. Anyway, again, it's just kind of, it's really oversimplified. So, so the next thing we're going to do is we talked about the quantity power. Now let's talk about its unit, which is called the watt. The what? The watt. Okay. So again, unit is a quantity that you just take and you adopt it as a basis or standard of measurement. And so you're basically calling it, you're coming up with a measurement system for the quantity, and you're calling it a unit, and the unit name is that thing. So W is the unit name for the quantity of power. And you can have 1 watt or you can have 2 watts, so it becomes plural. Remember that. And then you can actually go into the measurement of the unit itself, which describes how it's measured in using physics and physical quantities. The definition of the unit then is the unit of heat generation. And that does have some truth to it. Resistors dissipate power in the form of heat, so that's very important. Definition, that's the first one I actually found that had any value. Definition of the unit of measurement. Okay, the measurement of a unit is a definite magnitude of quantity defined and adopted by convention or by law. You know the rest, it's just a bunch of crap. So let's go through this. What is the measurement of the unit called the watt? Well, they take a unit of the electric power required to do work at the rate of 1 joule per second. It is the power expended when 1 ampere of direct current flows through a resistance of 1 ohm. Okay, I'd be sure to memorize that one. Okay, even though they don't define what a joule is. What's a joule? What's a joule? How many people know what a joule is? Joule of energy, you know. I don't think there's too many people that really understand that. There's a few people out there, but basically a joule can refer to lots of different things, so don't worry about that. It's nonsense. Okay, let's go to the next thing here. let's take a look at this chart. I showed you several formulas with the unit subscript attached. That's just because I had them already made up and I didn't want to have to redo them all again. It's kind of a handy thing to have until you actually learn all 12 of the formulas. So after you learn the 12 formulas, things change for you. So if you look at the chart, you would use only V, I, R, or P. You would never write the equation using units instead of the quantities. I've seen people actually do this where they'll take the units and they don't know the quantity, so they'll write the formula out in terms of the units. And some people don't know this, and they need to know that all you do when you're writing the formulas, you always use the quantities, the symbols for the quantities to write the formulas, always. Okay, so now let's go on to the next thing here. Now most people don't understand how to use the Ohms and Watts laws formulas. That's kind of what we're talking about, but we had to go through all that trying to decipher all this illiteracy for you so that you're not confused on everything you try to learn. So what they do is they learn Ohm's law typically. They learn the Ohm's law formula itself, which is V equals IR, and the Watts law formula, or P equals V times I. And they use those two formulas to figure everything out. They don't think it's necessary to learn all 12 formulas and you know, all 12 formulas and Watt's law and Watt's law and so forth. And you do need to know all 12 formulas in order to effectively use the Ohm's law system. And I'll show you why. I would estimate that probably 80% of the electronics engineers and electronics technicians don't know this or never realized that a better technique exists than what they're using. And they're probably real hesitant to try this for that reason, because it would be embarrassing. But each quantity, V, I, R, and P, have 3 formulas associated with them. So just take the circle chart here and write them out. Now don't write it out like this, where you got V equals IR, P divided by I, and square root of P times R. Don't write it like that. Just write out each one separately. V equals IR. Next one, V equals P divided by I. Next one, V equals the square root of power times resistance. And just write them out like that. Now just go through all those and memorize them. One thing you might want to do is put them all on index cards. That helps you memorize them quicker. It's the way to go. Okay, so now let's pretend like you've got them all memorized now. And so if anybody asks you, what are the Ohms and Watts laws formulas for current? You should be able to state what each of the 3 equations are. And so next I'm going to go through some examples with you. Alright, we're back. Take a look at this chart here. This is the big chart that you really have to know. The column on the leftmost side of the chart is the known values. I'm sorry, the known values. So V and I are known values. V and R are known, and so forth. All those are known. And then the formulas that you see off to the right, there's going to be 2 for each combination of variables that are known, and that's really what you need to learn in terms of Ohm's law. You'll see people that learn 1 or 2 formula, like they'll learn V equals IR, and then they think that they can figure it out, and well, you can't, because you don't know what the other variable is. Well, they say, yes, I can, I just have to figure it out. Well, while you're doing that, I'll have figured out about 6 different problems. So, and you have to be able to actually think about this stuff without figuring it out. That's the key to really using Ohm's law. So this chart here is really nice. This is kind of the ultimate goal, but there's a little prerequisite, kind of a gradient, as you will, kind of a step-by-step approach to learning this chart, and this will make it a lot easier. So take a look at this little yellow piece of paper that I've made up here with the different formulas and stuff written on it. Now you can see where I wrote. First thing you're going to do basically is you're going to have V and I as your known variables. And we're just going to follow down the left-hand column of the chart that I showed you. So the first one would be V, and then I would be the first possible combination of known values. And if you look on the yellow chart here that I made up, what I did was I wrote V, I, R, and P, and then I circled V and I because those are the known values. And then the key to understanding this is that V and I fit into the 2 unknown variables. So if I know V and I, then I know that R and P are going to be solved in terms of V and I. So that's how you really want to learn Ohm's law. That's the whole point of that's the whole point of it being such a great system, and it's why everybody kind of brags about it. But unfortunately, they don't teach it to you the correct way where it's actually useful like this. So let's go to the next one. The next possible combination, starting when we started with VI, so the next one would be VR, would be the next possible combination of known variables, VR. So if you look at problem 2 there, what I did is I wrote out VI, R, and P, and then I just circled V and R because those are the known values. Okay, and then I know that V and R are going to fit into the formulas that are used to solve for I and P. So I equals V divided by R, and P equals voltage squared divided by resistance. So if you go down to the next possibility, V and P, that would be represented on the third formula there. I circled V and P as being the known values. So now I know that V and P are going to be the variables used to solve both of the unknown variables, I and R. So I is equal to P divided by V, and R is equal to voltage squared divided by P. So and then we'll do one more here. The next one would be well, we got I and V. That's the same as the first one, but remember we're learning them in you know, back and forth. So we're learning both possible combinations. That's why there's 12. So we have VI. We'll also have IV. So you won't be able to like memorize VI, and you know you'll be able to look at it either way and understand it. That's what you really need to be able to do. So let's see. That one's fourth one is the same as the first one. Let's do. Let's say we know R and I. Let's see, where is that one in here? Yeah, it's on the. It's like the almost the first one to the last there on the top column. So the known values would be R and I, and then so you know that R and I are going to be used in the formula, both formulas for solving for the V and the P. So that's really the trick to using Ohm's law. That's why you will know any two values that you know, you will be able to find the other two values, not one value, two values. So that's why it's a lot better, because you just increased your ability to think and to do things by 50% by learning this. So now instead of thinking of two variables enabling you to find a third, you're going to be thinking in terms of two variables helping you to find the other two, because you're going to know exactly what the variables are. Because once you know the first ones, the ones that you know are going to fit into the other two for the equation, and that'll really help you. That's why I think you should do this first. Just practice doing this first, and then it'll be a nice little step-by-step approach to learning the chart. Don't try to memorize the chart. I think that'd be really hard. Just do it my way until you get all the formulas down really well, and then you can go ahead and increase your speed by going through and maybe making up some flashcards or something like that. So let's return to the video here that we were talking about, and I think I have a few more things to say and we'll be done. Alright, so once you memorize the formulas and you've practiced using this little system I made up until you get them down, you go ahead and take it. We'll take it to the next level. Once you get them down, then we'll take it to the next level. So take a look at this chart here. The quantities in the leftmost column are known values, and then to the right are the associated formulas. Now in the leftmost column, that's what we want to talk about. The leftmost column, you can see that there's 3 that start with V, there's 3 that start with I, there's 3 that start with R, and there's 3 that start with P. Now this is simply a list of all the possibilities that can come up. Now you definitely need to learn both ways. I just say all the possibilities. So the method you use to step it up a notch, in other words to learn it even better, is to simply make up or get yourself some 3x5 index cards and use them as flashcards. And so on your first index card you'd write V and I, and on the back you would write both formulas that you can use using those two variables. So if you want to effectively build electronic circuits, this will increase your efficiency by probably about 50%. Now, if you don't want to make up index cards or flashcards, just write the VIRP and solve some problems like I showed you. The advantage to using flashcards is you can mix them up and practice each possibility without missing any. So here's the chart again. Write it all down and use it as a reference, and then use that VIRP method I showed you to practice it. So to recap, then first thing you got to do is memorize the three formulas for each quantity, VIRP. So voltage equals current times resistance, voltage equals power divided by current, voltage equals the square root of power times resistance. Memorize all three formulas for each variable, V, I, R, and P. Then use the VIRP practice method to practice writing the formulas until you get good at it. And then use the chart as a reference, of course. And then use your existing flashcards. That'll help you a lot. Use your existing flashcards to go through each possibility of two known quantities while you practice using the VIRP system I showed you. That way you practice using each possible combination without doing it in the same order, each time. So you go completely through all the different possibilities on your cards, and then when you're done, shuffle the cards so they're in different order, and then practice the VIRP method again. Just go through one card at a time. Write it up on using the VIRP system I showed you. So this works for me, and I hope it works for you. I'm pretty sure it will work for you. Definitely help you to get better using Ohms and Watts laws, and that's what you need to know to be able to build your own circuits. And that's kind of the objective of my hobby electronics videos, is to actually enable you to build circuits as opposed to just looking at a schematic and sticking your probe in at the right number. That doesn't require too much talent, really. So don't forget to learn the basic series and parallel circuit rules for DC circuits before you start, trying to really apply this. And that's another series of videos I made. I would check that out if you're planning on doing a lot of this stuff. Check out that. Make sure you get all those down. And that's it. Hope you get something out of this. I'm pretty sure you will. Later.